Good afternoon, everyone. This is Nazirke. I'm a second-year PhD student at UC Santa Barbara, and I'm here to present our work, SQuadS. So, what the problems that we are trying to solve? Looking at the software and hardware worlds, we see some different trends that are a bit hard to manage. First, in the hardware world, because of the end of the Moore's law, we see that there are so many hardware advancement, and especially accelerators are becoming so prevalent. They can be special purpose, they can be general purpose, they can be tightly coupled, loosely coupled, and so many options. On the other hand, in the software world, we see that software stacks are getting so complex and heavy, like networking, virtual machine, isolation provided for the cloud applications, and actually some system services like malloc are getting so complex, and there are so many options for them to choose and to tailor for different application types. And we also see that some of the system services, like shown in the presentation, are having some hardware implementations as well. And what we see as a result is that not only hardware is getting heterogeneous, but also software is getting complex and a little bit moving down, showing that accelerators are becoming imperative. So, what are the existing solutions? We see some exciting works here, which are based on microkernels or also based on some OS proxies that are presented by Solros or M3. And we see that in some works like M3, there are some like hardware attachable on top of accelerators, or as they call coprocessors, that can do some light operations, but for the heavier ones, they would be always falling back to the host CPUs. And so, as we see in many of these works, this enables those accelerators to see, apart from the constrained physical address domain, to the virtual address domain, but they will be still relying to the host CPUs for many situations, and which we call your host first model. And we say that it's not a fully transformative, and that we need more different solution that will let us see hardware software co-design in a different realm and light. So before coming to a solution, we see some background info trend as well, that high-performance system services share some similar communication mechanisms, like network using shared memory queues to communicate between TCPs and user space applications, or garbage collection, sharing some heap space information between accelerators and the user applications. Also, malloc, even though it cannot be fully uploaded to accelerators, it uses shared memory queues for its fastest software implementations. We see that respective hardware for system services can communicate to the user space via these shared memory queues as a bespoke communication mechanism, but it is not yet implemented or realized to communicate between all these different mechanisms of system services in hardware. So what's the solution? We say that we can have a SQuadS as a solution, which is a self-serve system services, as a hybrid approach to access system services both from the hardware and host software for flexibility, scale, and efficiency. We say that to realize it, it is important to have common substrate between the all system services, for example, for garbage collection or page fault serving, and we say that we obviously need some hardware implementation of those system services, and we say that we also need a clear communication mechanism to talk between this hardware system service, its software service alternative, between the threads running on the CPUs, or maybe accelerators and accelerators themselves. So we also say that in an event when hardware service would be busy or not available or failing, software service should be always available to fall back. So what kind of requirements do we need on accelerators, given there would be some computation accelerator and system service accelerator available on top of the CPUs? We say that given accelerators usually cannot see out of the physical address domain, we first need to access virtual memory. And if we want to use shared memory queues, we then have to also save information about the queues and be coherent with them and so on. And so we need some sort of a wrapper. And what we present here is that our previous work cohort engine actually already presents that wrapper on top of accelerator, so to enable a virtual memory and coherency for the queues. We say that it has features already which is latency insensitive, works with as both tightly and loosely coupled accelerators, and best suited for stream-based accelerators. And what is best with this is that it will not put a pressure on accelerator designers without imposing any sort of a heavy interface. And it is orthogonal to any cache coherency. By coherency we mean only keeping track of the queues living in the software. What do we need for service substrate? So we have certain requirements, as we say, a minimum feature set. And as a minimum feature set, we think that we should have a cohort engine to enable that tracking of the software queues and actual access to virtual memory. And we think that we also need to have callback pointers to the software and SQuadS queue address as we refer to system services queue, and software queue as we refer to the queues on top of the computation accelerators. And Maple LSU is also so important because garbage collection or page fault and so other system services or networking, for example, usually parses through the pointers for its data structures. And maybe we need some other important engines that we want to, for example, discuss with the community here today at LATTE. And so we're gonna have also this fallback pointer, so in an event when system services will not be available, the application can automatically fall for the system service available in the software. So at the end, now developer has so many options to choose between hardware and software implementations, and write the code in a very easy manner with shared memory queues and our API, and also it will be very performant because it will let to use core general purpose cores more efficiently. Also, it will make accelerators or applications to not wait for only one point of host CPUs. So that's all with our presentation. Please let me know any of your questions in our GitHub thread or after our presentation.